Welcome back to the Deep Dive. We're here to take the fascinating sources you send us, dig deep, and pull out these incredible hidden histories.
Exactly. And today, our mission is, well, elemental. We're looking at world history through the periodic table.
Not kings, not battles necessarily, but the elements themselves, the building blocks.
And you find so much packed into those little symbols, don't you? Rivalry, war, love, madness.
Yeah.
It's all there.
Let's kick off with a classic childhood fascination. Oh, maybe a dangerous one. Mercury, element 80, Hg. I know the author mentions collecting it as a kid. From old thermometers.
Yeah, that silvery liquid metal is captivating. But that same element takes us straight to early American exploration, Lewis and Clark.
Okay, I think I know where you're going with this. Not just maps and compasses, right?
Well, not at all. They carried 600 huge mercury laxative pills. Seriously.
The legendary Dr. Rush's thunderclappers. Why on earth Mercury? Was it really the go-to?
It kind of was. Dr. Benjamin Rush, a big medical name back then, hero of the Philly yellow fever epidemic, he swore by it. Mercurous chloride paste.
And the treatment was intense.
Oh, yeah. You swallowed it until you basically drooled uncontrollably and had, well, let's just say aggressive purging. The idea was the mercury, this poison, would drive out the disease.
Even if it made your hair and teeth fall out.
That was often the side effect, yeah. If you lived, they considered it a win. Grim stuff.
But the strangest part is how it connects to today, right? The archaeology.
Because those thunderclappers did their job, the explorers left behind traces of mercury in their latrines.
Whoa, wait.
Yes. So modern archaeologists can actually pinpoint Lewis and Clark's campsites by finding these concentrated mercury deposits in the soil centuries later.
Wow. So the element's story is literally physically embedded in the ground.
Written right into the earth. It's amazing.
That really sets the stage. These elements aren't just abstract science, they're soaked in human drama. And maybe nowhere more than in the fights over who discovered what. Gilbert Lewis.
Lewis, the ultimate almost. Widely seen as the best chemist to never win a Nobel. He basically rebuilt the UC Berkeley chemistry department.
But his big contribution, it was foundational, wasn't it? Not just one flashy thing.
Exactly. He figured out the electron pair bond, how atoms actually share electrons to stick together. I mean, it's fundamental to how we understand chemistry today.
So why no Nobel? Too broad.
Seems that way. The committee back then really liked, discovering a new element, a single big breakthrough. Lewis's work was maybe too fundamental, too framework changing rather than one specific finding.
And this frustration, it leads to a really dark end.
It does. He died in his lab. Officially, heart attack. But the whole place smelled sharply of bitter almonds. Cyanide gas.
And the timing.
That's the chilling part. It was the same afternoon he'd had lunch with Irving Langmuir, a younger, maybe flashier rival who had won a Nobel and was working on the Manhattan Project.
So it leaves this awful question hanging there. Accidental, suicide, something else.
We'll likely never know for sure. Just this shadow over his legacy.
And that kind of snub, being overlooked for crucial work, it echoes with Lise Meitner, doesn't it?
Oh, absolutely. Meitner's story is one of the biggest injustices in science history. She was essential to understanding nuclear fission.
She was the one who realized what Fermi had actually done.
Precisely. Fermi thought he'd made heavier elements bombarding uranium. Meitner, with her physics background, realized no, he'd split the uranium atom, a world-changing insight.
She figures out fission, but her colleague Otto Hahn publishes it without her name.
Yep, published it without her, and the consequences were huge. She was a Jewish woman who'd fled the Nazis, so she was isolated, politically weak.
And the Nobel Committee.
They gave the 1944 prize for fission solely to Hahn, chemistry prize, overlooking her physics contribution, ignoring her circumstances, just erased her role.
Brutal. Did she ever get recognition?
Well, sort of. Hahn got the medal, but much later, element 109 was named Meitnerium, Emden, in her honor. A lasting tribute, at least.
So these intense rivalries shape science, but basic chemistry itself becomes a tool of war for Tabor.
Haber is such a complex, maybe terrifying figure. His big breakthrough was fixing nitrogen, taking inert nitrogen gas from the air, 80% of what we breathe, and turning it into useful ammonia.
The Haber-Bosch process changed agriculture forever, right?
Absolutely. Mass fertilizer production fed billions, probably the most impactful chemical process of the 20th century, you could argue.
Saved the world from starvation, essentially.
It did, but That same process made nitrogen explosives cheap and easy to produce.
Yeah.
Germany could suddenly fuel its war machine without imported nitrates.
And Haber himself, he didn't just enable it, he led the charge.
He went from feeding the world to heading Germany's chemical warfare program in World War I, weaponized chlorine gas. Horrific.
Yet he won the Nobel Prize in 1918,
Yeah.
even though the Allies saw him as a war criminal.
Caused a massive outcry. He had to go into exile for a bit.
Yeah.
The Nobel Committee sort of compartmentalized honoring this life-saving discovery, ignoring the man's wartime actions.
And the final awful irony.
Years later, Haber, who was Jewish, was forced out of Germany by the Nazis. And the insecticide formulation he'd helped develop, Zyklon A, was refined into Zyklon B,
The gas used in the death camps.
used to murder millions, including members of Haber's own extended family. It's just a chilling full circle. The element that feeds also kills.
A profound paradox indeed. And elements continued to be weapons. Tungsten, W or wolfram, World War II.
Tungsten. Super hard, incredibly high melting point, over 6,000 degrees Fahrenheit, perfect for armor-piercing shells. The Nazis needed it badly.
And the main supplier was neutral Portugal, under Salazar.
Salazar played it brilliantly, some would say ruthlessly. He sold tungsten to both sides, Axis and Allies, jacking up the price.
How much did it go up?
Astronomically, from around $1,000 a ton to $20,000 a ton in just 3 years. He made a fortune playing the Maffei chess.
When did he finally cut off the Nazis?
Only in July 1944. After D-Day, when the Allies basically forced his hand with serious threats, he had milked it for all it was worth.
About $170 million in personal profit, wasn't it? Built on this critical war element.
Yeah, a staggering sum back then. But the fight for hard metals wasn't just WWII. Go back to WWI, molybdenum.
Molybdenum, right below tungsten. Needed for steel alloys. Artillery.
Exactly. And the hotspot wasn't Europe, it was Colorado. A single, struggling molybdenum mine in the Rockies.
Run by a banker, Otis King, who
Right.
was apparently mining too much.
Yeah, he was flooding the market, crashing prices. German agents were actually sent to sabotage his mine. It sounds like a spy thriller.
What kind of sabotage?
Threats, equipment damage. The sources even say King himself was thrown off a cliff by agents.
Seriously?
Landed in a huge snowdrift, apparently. Saved his life. It shows how desperate the resource wars were, even back then. A
Alex,
literal fight over rocks.
With all this violence and greed wrapped up in elements, can any element be just pure? Perfect.
Chemically, yes. Look at the noble gases, group 18. Helium, neon, argon.
They don't react much, right? Chemically aloof.
Exactly. Full outer electron shells. Satisfied? Stable. Plato talked about ideal stoichia or elements, and these guys kind of embody that.
And helium does something especially weird when it gets super cold.
Oh, yeah. Cool liquid helium down below, about minus 452 Fahrenheit. It becomes a superfluid, zero viscosity, zero resistance.
Meaning?
It flows without friction. It can even climb up the walls of its container and flow over the edge, defying gravity. It's like a physical manifestation of a perfect ideal state you usually only see in equations.
That sounds almost magical. But then there's the flip side. Elements causing pure misery. Cadmium.
Cadmium. Responsible for the Itai disease in Japan, 1930s, 40s. Means ouch, ouch disease, literally.
Because of the pain, what did it do?
Horrible joint pain, brittle bones, kidney failure. Mostly affected rice farmers, often women. The source mentions a doctor breaking a patient's wrist, just taking her pulse. The bones were that fragile.
And the cause was industrial pollution.
Cadmium runoff from zinc mines got into the Jinzu River, then the rice paddies. The farmers ingested it through the contaminated rice.
But why did their bodies absorb it so readily? What's the chemistry?
That's the tragic part. Cadmium is chemically similar to zinc, which is essential for the body. These farmers were often malnourished, low on zinc,
So their bodies were desperate for zinc.
and mistakenly grabbed onto the toxic cadmium instead, absorbing it at dangerous levels. A terrible intersection of pollution, chemistry, and poverty.
Such a stark contrast to the perfect helium. But elements can also correct imbalances, right? In the mind. Lithium.
Lithium, element 3, often associated with the poet Robert Lowell. Cal, they called him. Famous for brilliant poetry, but also extreme manic depressive episodes.
The whole mad genius trope, believing he was the Virgin Mary trying to stop traffic.
Exactly. His behavior was erratic, sometimes dangerous. The public often linked his genius directly to this instability.
But chemically, something was off. And lithium carbonate, the simple salt, could fix it. How?
It's not like an antibiotic killing a germ. Lithium seems to regulate the brain's internal clock, interacting with proteins involved in mood cycles. It helps stabilize those extreme swings.
So it worked for Lowell. It calmed the cycle.
It did. He became much more stable. But he lost the highs, the intense manic energy that some felt fuel his creativity.
What was the consequence?
A friend described him afterwards as seeming like something transferred to a zoo. Tamed, maybe diminished. It raises that old, difficult question. Can you separate the genius from the chemical imbalance sometimes? Do you lose something vital when you stabilize?
It's a heavy question. So from Lewis's ambition to Haber's paradox, tungsten wars, cadmium's poison, lithium's calm, the periodic table really is a map of human history.
It really is. Every element has stories.
Yeah.
But just when you think you've got the map figured out, there's a twist. Let me throw one last thing at you to wrap up. Superatoms.
Superatoms, what are those? Like giant new elements?
Not exactly. They're clusters of existing atoms. But when you arrange them just right, the whole cluster acts chemically like a single atom of a completely different element.
Wait, acts like or is like?
Chemically, functionally, they're identical. Because the cluster achieves the same outer electron configuration, the key thing that determines chemical behavior.
Okay, give me the example. The really mind-bending one.
The 13 aluminum atoms grouped together in a specific structure.
Yeah.
And that cluster of 13 behaves chemically exactly like one single atom of bromine, a corrosive halogen.
13 aluminum atoms are bromine, chemically speaking.
In terms of how they react, yes, same chemical personality. It
Yeah.
blows your mind a bit, doesn't it?
It really does. It implies the table isn't necessarily final.
Exactly. If clusters can mimic elements, what does that say about the fundamental building blocks? Are there other elements out there, hiding in plain sight, just made of different combinations? Something for you to think about until our next deep dive.